Hi, and welcome to this presentation from Mr. G on scientific notation mathematics. One of the things that we have to be successful at in order to do chemistry is scientific notation. And before we even talk about scientific notation, one of the things that we want to understand are basic exponents. So that's going to be the background knowledge that we're going to cover on this slide. So let's talk a little bit about exponents first. So let's take an exponent with base 10 and raise it to the first power. What does that equal? Well, when I take 10 and I raise it to the 1, what I'm doing is I'm just saying I have 1 10. So it just equals 10, right? Let's take a different example. If I have base 10 and I raise it to the second power, what am I saying? I'm simply saying I have 10 times 10. And what is 10 10 times? We know that's equal to 100. Maybe I'm refreshing your memory now. Let's do it again. I have base 10 and I raise it to the third power. What does this mean? It's the same thing as saying 10 times 10 times 10. I've multiplied 10 by itself 3 times. 10, 10, and 10. That's what the exponent means. 3 times, I'm multiplying 10. What does that equal? It means it's equal to 1,000. Okay, so 10 to the 1, 10 to the 2, 10 to the 3. The one exponent that I want to talk about right now that we're going to want to think about a lot for this presentation is going to be this one. What does it mean when I raise 10 to the 0 power? Well, maybe you'll recall that when you raise anything to the 0 power, it could be 10 to the 0, it could be 1 to the 0, it could be 3 to the 0. All of these things are going to equal not 0, but 1. Now the reason for this is a little bit convoluted, and we could go through proving it, but for now, let's just remember that whenever you raise something to the 0 power, it always equals 1. And this is going to become important for understanding scientific notation math for our purposes. So let's do an example of what a scientific notation problem will look like, and this will get us to the point where we can move forward. So if we know that 10 to the 1 is the same thing as 10, then let's say I have something like this, 2 multiplied by 10 to the 1. Well, what's that going to equal? Well, I've shown up here that 10 to the 1 is the same thing as 10, so I can rewrite this as 2 times 10, right? Well, what is 2 times 10? 20. Right? Okay. So we don't want to let the exponents scare us. We just want to remember what they mean. Okay? So let's go to the next slide and talk about what scientific notation is and why we use it. Scientific notation math is used in science for a reason. What we deal with in science a lot of times are either really big numbers, like the number shown here, or really small numbers. And you can think of maybe some examples of this, right? Say you're a geologist and you are measuring the mass of the Earth. Well, that's going to be a pretty big number, right? Or maybe you're a chemist like myself and you're measuring the mass of an atom. Well, that's going to be a really small number, isn't it? Well, these are numbers that are going to have a lot of zeros if we try to write them out in, say, grams or milligrams. Maybe it'd be better if we use different units of measurement, but we'll talk about units of measurement later. But if we use the units of measurement that we're used to, we're going to have a lot of zeros with those numbers, either in front of our decimal or behind our decimal point. And so it's more convenient if we can write those numbers in a different way. And that's where scientific notation comes in. We can either condense those numbers down using exponents, like we talked about on the last slide. Specifically, exponents with base 10. So let's see how this is going to work. And you might remember this a little bit as we start to talk about it. Our first objective is going to be to locate where the decimal point is in our number. And so for our really big number here, we find our decimal point, and it's all the way at the end, right? So what we're going to first do is we are going to count by doing these little U marks how many place values that decimal point is away from being in between the first non-zero number and the digit next to it. So what do I mean by that? Well, I want to look and see that this 2 is the first non-zero number in the entire number, right? And so I want that decimal point to be just to the right of that first non-zero number. So I've done my little U marks. Now I want to count how many U marks there are. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15. And what that means is that that number of marks, or number of place values I had to move my decimal point away, is going to be the exponent of my base 10. And what I can do now is I can take all those zeros away, and I can just write the non-zero numbers with the new decimal point position in place. I can now not forget to write my unit of measurement. And this becomes my number in what I call condensed notation, or scientific notation. I call this expanded notation. Now let's see what this looks like for a number that's really small. Well, here we do the same thing that we did in the last problem. We count how many place values it takes to get our decimal point in between the first non-zero number and the digit next to it. This time we're moving in a different direction though. Okay? So if I do my counting, it just so happens it's the same number of places that I had to move. It's just in the opposite direction. So my number is still 2.9 times 10, and I still have to put a 15 up here. But guess what? This time it's going to be to the negative 15, and it's seconds. So how do I know whether I put a negative sign or if I leave it positive? Well, there's a little trick that I'm going to teach you that'll help you know. Once we get all this written out. So here's how we know. What we did was when we moved our decimal place, we had to move it to the left, right? When we moved our decimal place here, we moved it to the right. Correct? Now, when our number is in expanded notation, it's like saying our number here, I'm going to rewrite it, is just like this, times 10 to the what? 0. That's why I taught you that in the last step, right? Because that's the same thing as saying times 1. Which is why we can leave it off in the first place, right? Because any number times 1 is itself. So that's why it's never written at all. Because why write it if it's really not necessary? So why am I writing it here? Well, let me show you. There's a reason I'm writing it here. It's because it'll help this concept make sense. So if I'm at 0 with my exponent, and I'm moving my decimal point to the left, what I'm doing to my exponent is I'm making it larger in value. So 15 is larger than 0, right? So I'm making it larger in value. I went positive with it. Well, here I went to the right, which meant from 0 I had to reduce its value. I had to make it more negative. So the saying is to help you understand, am I making it more negative or am I making it more positive? And so if you're moving your decimal point to the left, your exponent should always become more positive from where it started. We know our exponent started at 0, so we should be making our exponent more positive from 0 by 15 units. Right? So if we start at 0, we're adding 15 because we're coming more positive, larger. Leftward, larger. Rightward movement for our decimal point means we're going to reduce the value of our exponent by 15 units, making it more negative. Okay? So that's what this is telling you here. So if you can remember that, then you'll always get these right. And this is probably the number one mistake I see most in this entire class with chemistry, is individuals not understanding this concept and not implementing this correct. So if you can get this down now, you're going to be squared away. So we'll get some practice with that, okay? One of the things that we do in this class is we don't use scientific, or I should say graphing calculators, okay? Why? Because they keep you from understanding the concept of what we're doing with the math. 2, because on your standardized tests that you take, if you're headed off to college and beyond, most of them rely on you not using a graphing calculator. They rely on you understanding the basic concepts behind the math. And if you look at all the problems, this is coming from someone who's coached people in SATs and other types of standardized tests, You're going to do much better on those tests if you can understand how to do these problems without a calculator at all. You'll be faster, you'll get the problems right more often. You want to understand the concept behind these problems, and if you can do this math without a calculator, which is actually really easy once you get a hang of it, you're going to be so much better off. And I'm going to teach you the strategies in this class on how to do it, and we're going to practice them a lot. And so don't let it intimidate you. It's really not that bad. You're just not used to it because you've been trained to use these graphing calculators, and you've been conditioned to just push these buttons to do it for you, which is doing you a disservice. So let's get this done right. You'll be thankful that you've learned how to do it, and it's going to pay off in the end. There's two very easy strategies to do math with scientific notation. There's one strategy if we're doing problems with addition and subtraction, and there's another strategy for multiplication and division. And so I'm going to teach you the strategy for addition and subtraction first. Then I'm going to teach you the strategy for multiplication and division. We'll practice them separately, and then we'll combine the problems together to make sure that you've really learned them and understood them. All right, so let's talk about how to do scientific notation math without a calculator when we're doing addition and subtraction. So there's always going to be some steps involved when we're first learning these, and then once you get it down, you'll just kind of fluidly do it on your own. So what we want to do when we're doing addition and subtraction with scientific notation without a calculator is you want to make sure that our exponents in the numbers that we're adding or subtracting are the same value. Okay. So I'm going to say that again. We want to make sure that the numbers that we're adding or subtracting have exponents that are the same value. So, if we look at our example here, are they the same? Well, we have 2.4 times 10 to the negative 4 meters plus 1.2 times 10 to the negative 3 meters. So, our exponents of base 10 are not the same value. So what do we have to do? Well, we have to have them the same, so our option is to use what we've learned in the last couple slides to make them the same. Yes, we're allowed to do that. We can make them the same. Once we've made them the same, then we can add them together. That's all we have to do. Okay, so there's two ways to do it, really. You can, whoops, let me fix that. You can either make the negative 4 a negative 3 by moving the decimal in this number, or we can make the negative 3 a negative 4 by moving the decimal in this number. Doesn't matter. I'm just going to change this one, okay? That's just what I'm going to do. So, let's do it. So if I want to make negative 4 and negative 3, we ask ourselves, okay, is that making the exponent larger in value, or is it reducing its value? Well, we're taking a negative number, negative 4, and are we moving it down the number line, or are we moving it up the number line? Well, we're moving it closer to 0, so that's making it larger in value, right? So that is a leftward motion of our decimal point. So if that's a leftward motion of our decimal point, then that's what we're going to do to change our number. So this is going to become 0.24. Whoa, what happened there? Let's fix that. Times 10 to the now negative 3 meters plus 1.2 times 10 to the negative 3 meters. Okay? Now, I'm not really being specific about what, decimal place to round to or anything like that. So when we do chemistry math, we like to do it vertically for a reason that we'll learn later. So I'm just going to set it up vertically, and I'm not going to really tell you why because it doesn't matter at this point. But we'll set it up vertically. And so what we do now is we just kind of have the exponents to the base 10 just sitting out here, and we do our addition. And then the numbers we add are just the numbers here. And then we use the exponent that we started with, times 10 to the negative 3. You don't add these, you don't subtract them, they just stay what they are, times 10 to the negative 3. And that is your answer. See how easy that is? Okay? And that's how we do it. And I kind of combined these steps here, but I'll reveal what step 2 was. So step 1 was this part here, changing the number to make it the same. And step 2 was this part here, doing the addition and getting our final answer. And that applies to both addition, this was of course addition, but also subtraction. It would be no different for subtraction. I will add one thing to this. Whenever we get an answer and the decimal point is not just to the right of the first non-zero number, we want to move it there and we want to change our exponent accordingly. So we want to always make sure our final answer is in proper scientific notation. So let's say we had 4.4 times 10 to the negative 2. All right, that's not proper scientific notation. I'm sorry, it would have been to the 5. Let's change that. Oh dear. My pen is running out of juice. To the 5. And so what we'd want to say is, okay, I need to move this decimal to the left. I need to make my exponent larger. I need to move it up the number line. Still, I had this wrong. Goodness. 4 is what this should be. And so by making it larger, my negative 4 would then need to become negative 3. And that would give me my final answer, right? 1.44 times 10 to the negative 3. So that's what I mean by making sure that our final answer is in proper scientific notation. So if we end up doing our math and we get that, then just make sure you change it to this before reporting it as your final answer. Okay, so we're going to do now the multiplication and division versions of scientific notation math without a calculator. A little bit of a different set of rules, but it's still not so bad. So the first steps for these are a little different. Instead of worrying about the exponents being the same in the numbers that we're doing math with, we just go ahead and just do our math first. So I'm going to do an example of multiplication, And then I'm going to do an example of division because we handled the two just a little differently. Not much, just a little differently. Okay? So what we do for both of them, regardless of the type of math, is we perform the given operation with what we call the front numbers first. Now what I mean by the front numbers are these guys, okay? The numbers without exponents of base 10, okay? So here, in the multiplication side, we're going to just straight up multiply 2.4. Oh boy, what did I do there? I'm going to multiply 2.4 by 1.02. And we're going to get I'm just going to round, 2.4. It's 2.448, but I'm just rounding, okay? On this side, if I do division, I'm going to do 1.8 divided by 5.1. And if I round, let's just say 0.35. It's 0.3529, but I'm going to do 0.35. All right, so those are the numbers that I end up with if I do the operation that's given with just those quote-unquote front numbers. Now, we can't forget about our exponents, but that's what we do next. So that's step one. Now's where we deal with the exponents. So this is where the two are a little different. So multiplication, we deal with the exponents by adding the exponents up. Division, well, we subtract them. That's the difference. So how do we handle it? Well, let's look at the multiplication first. So I have a 5 and a 10, so I'm just going to say 5 plus 10, right? 5 and 10. What does that get me? It gives me 15. So what I do is I say, okay, 2.4 times base 10 to the 15. Now, where am I getting this unit of grams squared? Where's that coming from? Well, think about it. You've got a gram for this unit, a gram for this unit. What are you doing? You're multiplying grams times grams. Well, G times G is G squared. Okay, so that's how you get your units if you're multiplying to. That's important. You need to know how to do that. All right, let's look at division. If I'm subtracting, I have 7 minus 12, right? 7 minus 12 is negative 5, all right? So it's the same situation over here. So I got 0.35 times 10 to the negative 5. Oh, but look, I'm not in proper scientific notation. So what do? I move it over to the right one. That's a reduction in value. So I need to make it more negative. 3.5 times 10 to the negative 6. Okay? Why don't I have a unit of measurement? Shouldn't I write a unit of measurement? Well, liters divided by liters, the liters cancel out. No unit of measurement. Okay? So you got to think about your units carefully when you're doing multiplication and division. They're a little trickier. All right? Be careful when you're doing exponents and the math here, because what if this was a negative 12? Well, then it would be 7 minus negative 12. Well, when you're subtracting a negative, what are you really doing? Well, you're adding, so your math would really be 7 plus 12, and you would get a different number. So just be careful, okay? Make sure you're careful what you're doing. All right, so you're going to get some practice with this. There'll be a lot of practice. As you'll know, and you'll find out in chemistry, it's kind of like a math class with a lot of concepts. We practice, and that's the only way you really get good at things. So don't be afraid to ask for help. If you need to do a specific conference with me, again, ask for help, but use the chats, use each other, use me, and make sure you get good at this now, because when we start adding it along with the chemistry, you don't want to be lost on this part. All right?